Exercise 843 is trying to get us to identify what mechanism a series of reactions will happen by. It's not asking us to draw the products just yet, but it is asking us to identify the mechanism that the reaction is likely to happen by. And the substrate they give us the name for it. The substrate is going to be 2-bromo-2-methylpentane. While the backbone name is the pentane, it's what comes after the last branch, that last YL. So pent means you have 5 carbons, so 1, 2, 3, 4, 5. I'm drawing the molecule, so I get to decide how to number it. I'm going to number it left to right. Now in carbon number 2, we have a branch. It's a bromine. And on carbon number 2, we have another branch. It is a methyl. So that is 2-bromo-2-methylpentane. And what you'll notice is the leaving group here is on a 1, 2, 3 is on a tertiary carbon. The leaving group is on a tertiary carbon. That carbon that the leaving group is bonded to 3 other carbons. So it's tertiary. Well, that means, if that's tertiary, that means that we'll be dealing with, in this table that we built up in a previous video, that means we'll be dealing with this third row in this exercise. And we'll see what mechanism we get when we combine that substrate with different nucleophiles and bases. Now in all of these, we'll be dealing with 2-bromo-2-methylpentane. And so we're going to leave this row. That will be the only row we consider in this exercise. So here, what if the base or the nucleophile was ethanol, ETOH? Well, that's really ROH, right? The F is, the ET is just a carbon chain. It's an ethyl group. And so that acts like the R. So what we have is a weak base and a weak nucleophile. And we can see that that overlaps with the leaving group being on a tertiary substrate. That gives us our mechanisms. We will both have the E1 mechanism and the SN1 mechanism. So we'll get products through both of those mechanisms in that reaction. Well, what if we have TBUOK, Potassium Tert-Butoxide? Well, that is really like this. The tert-butyl group is like that. We have an oxygen attached to it, negative, and a positive potassium. This is really the base, and that is this RO group that we see here. Now here in this table, it's paired with a sodium, here it's paired with a potassium. That doesn't matter, that's just there to stabilize the negative charge. So what we're dealing with is a strong base and a strong nucleophile. And so the only mechanism we'll get here is an E2 mechanism. So the product that we'll get will be the product that we'd get through an E2 mechanism. Okay. Well, how about the next one? What if we have sodium iodide? Sodium iodide, that is a weak base, strong nucleophile. A weak base and a strong nucleophile, leaving group on a tertiary carbon, will only give us the SN1 product. What if we had sodium ethoxide? Sodium ethoxide is a strong base and a strong nucleophile. We could see it right here. And so if the leaving group is on a tertiary carbon, that will give us an E2 mechanism. So the product we get would just be the E2 product. Finally, if we have sodium hydroxide is also a strong base and a strong nucleophile. So because we have the leaving group is on a tertiary carbon, if we combine that with a strong base and a strong nucleophile, we will only get the E2 products. All right, so this is our last exercise. This and the previous two were all just getting us used to using this table. In the next exercise, we're going to use this table to identify the mechanisms, but then we're going to use the mechanisms and our knowledge of them to draw the products. A powerful step in being able to synthesize any compound we want.